Good evening to all of you. Today we'll see about the fluid statics chapter. Now it is the second module's first lecture we are going to start. In the fluid statics, we are considering the fluid element under only normal component of the force. In that case, no shear component will be acting there because shear component is only acting whenever the fluid is in motion. So our consideration, the fluid is at rest. Now, a slight recapitulation will do it. Whenever over the fluid element, how many types of the stress component is acting, and in case of the fluid statics, which are predominant in that case. So accordingly, we'll start it one. So we'll come to the slide and we'll go forward regarding the cases. So the fluid statics chapter. Previously, the normal component of force we have seen, that is the pressure. What does it mean by the pressure? In macroscopic point of view, the pressure is the time average force per unit area. We know that is the pressure from the macroscopic point of view. So here, before going to the pressure is a combination of the normal stresses. Is the average of three normal stresses in the opposite direction. So let you see here is the x-axis. We have seen it previously. We are considering it 1. Is the y-axis, considering it 2, and z-axis, considering it 3. So if you consider this surface plane, if you consider this surface only, so in this surface, how many stress is acting normally? One stress is acting, that is the normal stress, outward side. That is, we are knowing at the tau 11. So tau 11, the first, we are considering it as a tau Ji term, where the J will gives you the normal to the area, normal direction to the area, normal direction to the area. And this I will gives you the direction of the force. Direction of force. So here, this component, actually, this is a surface. This surface, if you draw the normal line from the surface, outward normal, that will along the x-axis. So that's why it is first one, and second one, because the direction is also in the x-axis. So that's why tau 1. Just a bit of recap. Second stress component is acting in this way. That is the shear component. That is nothing but tau 1, 2. Tau 1 is a common because the same surface it is acting. That's why tau 1, because first indices denotes the normal direction to the area. So that is for the same, because area is not changing, the same area we are considering. And in this way, in this side, tau 1, 3. So from the surface we are getting tau 1, 1, tau 1, 2, tau 1, 3. Whenever the fluid is at static condition, so fluid at rest, that time no shear component, no shear component will be acted over it. So this component and this component, both are 0 in that case. That we are considering about this surface area. If you're considering now this surface area, top surface area. So top surface area also normal force is acting top side. That is tau 2. If their shear force is acting, then how it will be looks like, this will be in this side, that is known as tau 2, 1, and this side tau 2, 3. But these two components are not there, only normal component is existing. The same way in the tabulate formula, if you write it down here, tau 2, and tau 2, 3. So here also, this component, CR component is 0, this CR component is 0. So this is existing, this is existing. Similar way, if you write in the other surface, in this surface, the same way you are getting the tau 3, 1, tau 3, 2, tau 3, 3. So here also, this component becomes 0, this component becomes 0. So only existing component when the fluid is at rest, the only existing component is tau 1, tau 2, and tau 3. These three components are only existing. So what is the concept of the pressure? Pressure concept is coming. Actually, pressure is the two types of the pressure. One is the mechanical pressure, another is the thermodynamic pressure. So mechanical pressure is defined in such a way, the average of these three normal components in terms of the negative. So it can be defined in this manner. Average of these three. And why it is negative? The concept of negativity is coming because you see here tau 1 is outwards normal. So it is a tensile in nature. This tau 1, tau 2, tau 3, all are in tensile in nature. Whereas the pressure is considered as the compressive in nature. Now these shear components are just as tensure. It's a tensure, second order tensure. Better to say, it's a second order tensure. But what about the pressure? Whether pressure is a scalar, vector, or tensor, we'll see it on the next portion. We are confused with it. It is a combination average of these three tension forces. But whether the pressure is a scalar, vector, or tensor. This is now the scenario in here. So you take one component, this element here, like this way, one triangular element where it is the 90 degree. This angle is the 90 degree. So here in this surface, some pressure is acting. Let the surface you take it as let you take it dy. Length of this element dy. Length of this element you take it dx, and length of this element dl. So better to give some name here, A, B, and C. Whereas the AB is dl, high potential. AC is the here dy, and BC is dx. Now you consider it. So from here, some pressure is acting. Let you take the pressure is the Px. Pressure is acting. In this side, some pressure is acting Py. Because pressure is a compressive in nature, so direction is towards the element. It is acting. And from here, let you take some pressure is acting. So three direction, three pressure is acting. That is it. Px, Py, and Pl over the elements. Now, what is the force is acting? Pressure is a time average force per unit area. So if you multiply with the area with the pressure, so you will get the force. So here, what is the force is acting? Px into dy. Let you take perpendicular to the plane, it is the unit is there. So 1. So into 1. So better to write it Px into d. Here Py into dx into 1. So better to Px into 1. Here Pl into d. And this angle let you see take any angle is theta. This angle is theta. So sine theta, you will get it. The sine theta is equal to dy by d. And cos theta is equal to dx by d. So hence you are getting it. dy dl sine theta dx dl cos theta. Now you have to do the force balance. Now you consider here fluid is at rest. Your consideration is fluid is at rest. So whatever the force is acting along x-axis and y-axis, that will be under equilibrium. So net force should be zero, whether the fluid element is in equilibrium. Fluid is at rest condition or static condition. So net force along x-axis should be zero. Net force along y-axis, that also should be zero. So net force along x-axis. So along x-axis, if you take along x-axis, what are the forces acting here? So surface force, actually force means surface force plus body force is the net force. They are self-explanatory, is equal to zero. Surface force means the force is acting over the surface. The pressure is acting over the surface. So it is a surface force. Body force means, so body force is acting about the center of gravity. Body force is acting about the center of gravity. So in this case, along x-axis, there is no body force is acting. Along x-axis, there is no body force is acting. Okay. In that case, no body force we are mentioning. We are not mentioning even the weight of the element also. Because this element we are taking from the horizontal force. We are not considering any body force along x-axis and y-axis. It may be in z-axis, but we are considering here along x-axis and along y-axis. So surface force is acting along the x-axis is px dy. Is negative x-axis. Now this force, if this angle is the theta, so perpendicular to it this and perpendicular, so this angle is also the theta. So this side will comes the sine component, so PL dl sine theta. This side will come PL dl sine theta. So plus PL dl sine theta. Plus body force, we are not considering along x-axis, there is no body force. Is equal to zero from the equilibrium concept. Already you have seen dy is equal to dl sine theta here. So we are getting a thing px is equal to pl from this equation. Px and pl is equal. On the similar manner, along y-axis, if you are getting it. So surface force, what is acting here? So py dx is upward side, so it is a positive values. Py dx upward side minus this cos component will come pl dl minus pl dl plus no body force along y-axis also. So along x-axis we are not considering any body force. Along y-axis also we are not considering any body. And dx and dl cos theta is the same here. We are getting it py. So what is the ultimately thing we are getting it? Px is equal to py is equal to p. This law is the Pascal's law. As there is no body force is acting over it, the pressure what is acting over the element all are equal and direction insensitive. The pressure is direction insensitive. It does not depend on the direction here. On the Pascal's law you will get it. It having a magnitude, definitely the pressure having magnitude, but it does not have any direction sensitivity. And no area direction sensitivity also. The orientation of the area, it is not varying with the orientation of the area. So it is no more direction sensitive. It is no more the sensitive to the orientation of the area. So only it depends on the magnitude. So the pressure is a scalar quantity. So the pressure is the scalar quantity. So the pressure is a scalar. No doubt about it. So previous we are talking about, so pressure is definitely a scalar. It is not a vector because it's a direction insensitive. It's not a second order tensor also because it does not depend on the orientation of the area. So that is about the Pascal's law. But further, there is acting some gravity force. So there is some body forces there. Let you take the consideration. So this is the x direction, let you take. This is the z direction. And another direction you can take is the y. So z direction is, along the z direction, there is a gravity support. Along z direction. So along z direction, the gravity is the body force. In such a situation, how the equation will come? So again, you can consider first, the pressure is maybe the function of x, y, and z. Pressure is a function of x, y, and z. As it is a function we are considering, though it is not just assumption we are taking it. The pressure is a function of x, y, and z. So along x-axis, the pressure is changing. So that means if you take it the x coordinate, it is the z coordinate. So there is some pressure is acting px. Px. Here, because here some values is there. This distance is, let you take the distance is the del x. So here the pressure is acting x plus delta x. X plus delta x. If you know the Taylor series expansion, what does it mean? Because Taylor series expansion you see is a function of x. Let anything function of the x plus h. If you do the Taylor series expansion, it will be looks like this. As x plus higher order terms will come in this. In this way, the Taylor series expansion we are doing. The same way, the x is changing here. Previously, there is some certain x value. Now here it is the x is changing. So if you do this, the Taylor series expansion wise, the px plus del p del x. Why del p del x? Because pressure is a function of x, y, and z. So partial differentiation will come into the picture. So del p del x into the first order plus higher order terms we are not considering because x is very small quantity, so higher order is not at all we are considering. So pressure is varying in this way. Similarly, y direction also. and Z direction also. So Z direction also, let you take in this Z, some PZ is acting. Here Z is changing how much? So Z is changing, let you take here, Z is changing delta Z. The delta Z. And Y direction, delta Y. So actually, so what is the pressure at here? The pressure at here is the PZ plus delta Z, which is nothing but PZ plus dP plus higher order terms. Now the fluid is at static condition. The fluid is at static condition or rest. At rest. That means net force should be 0. So body force plus surface force should be 0. Along x-axis there is no body force, but along z-axis there is a body force. That's the G, gravity. So G is the body force. So if you consider along x-axis, just we are considering along x-axis, what are the forces acting here? Surface force, Px. So Px is positive side acting. Px is the pressure into area. Which area? Del Z, del Y. Del Z, del Y. Del Y we cannot see. It is a perpendicular to the plane. Del Y. We are not going. It's not equal. Minus Px plus del P, del X. Px. Higher order terms we are not considering because it's too much. So del Z, del Y. The same surface. That side also, whatever the surface, the same surface in that side, that is the surface force. Plus no body force along x-axis is equal to 0. So hence we are getting from this equation dP dx is equal to 0. That means P is not a function of x. Very minutely you see. As there is no body force, P is not a function of x. So if you vary the x, the P will not vary. It says that if you vary along the x-axis, there is no variation of the pressure. So the same Pascal's law is coming back in this way, as there is no body force. Similarly, along y-axis, if you see, y-axis also, if you see the same way, it will come py. We cannot see this thing py because it is a perpendicular to the plane py, but surface you can consider del x, del z, del x, del z. Over this surface, py is perpendicularly acting. Minus same way the py plus del p, del y. Same equation we are writing in different way. Del z is equal to 0. So from here also you are getting del p, del y is equal to 0. So p is no more a function of y. P is not a function of x, p is not a function of y. So p is only function of z. So partial differentiation of dp dz will be equal to the del p del z will be equal to this ordinary differentiation, because p is the only function of z, not a function of x, not a function of y. We'll see it just now. Now along the z direction, we'll see the scenario here. So along z direction is the most important thing along z axis. So along z axis, so pz is acting over pz into del x, del y. Del x and perpendicular to the surface is the surface, del x, del y surface. Minus, that is the surface force we are talking about. Pz, del p, del z. Now we are writing del p, later we will change it to the dp. Del z. into del x del y. That is a surface force plus body force is acting. Body force in terms of the is opposite direction, minus. So minus. Body force per unit mass is G. Body force per unit mass is G. Or gravity. Gravitational acceleration, we know it. So what is the mass of this system? Rho into volume. Rho is density of the fluid element into volume. So volume is del x, del y, del z. Density into volume, mass into acceleration or body force G. So this is the body force plus surface force is equal to 0. So you are getting the equation minus del P del Z is equal to minus del P del Z is equal to rho G. It is not 0. So hence we can conclude that P is a function of Z. And only Z, not X, not Y. So better way you can write it dP dz is equal to minus rho G. dP dz is equal to minus rho G. This equation is the very, very important and law of hydrostatics also we are telling. We are telling it as a law of hydrostatics also. So dP dz is equal to minus rho G. Most important equation. P is not depends on the X because there is no body force. P is not depends on the Y as there is no body force, but P is depends on the Z. And what is the dependency? dP dz is equal to minus rho G. That is the dependency. So, fresh way we are writing it here. dP dz is equal to minus rho G. Whether rho is a constant, density is a constant, G is a constant. We don't know. But if those two are constant, if density is a constant and G is also constant, then it's a constant term. So your equation will comes in this way, rho G dz, and if you do the integration, so rho G will come out from the integration only. Then it will give you the simple thing. Now, if you consider the free surface, free water surface, this is along z-axis. This is along z-axis. So if you go from the free surface somewhere else in this point, let you consider here some point A. You go from free surface to here. So A distance, let you take the distance is the H. You go H. At the depth of the H from the free surface if you are going. So initial, so what the pressure will be, whether it will be rise or decrease. So free surface, there was atmospheric pressure. Your initial was the free surface, atmospheric pressure. You take it as 0. And you are going depth minus H, 0 to minus H. What is your pressure? P. That is the limiting of your equation. So your integration, here you can only put integration because you are considering Knudsen number less than 0.1. So continuum hypothesis is valid here. That's why integration, differentiation, everything is possible. You can do. Okay. So P minus P and rho GH. That means the pressure at here, pressure at in this point, the pressure is more than the pressure of free surface. Free surface atmospheric pressure PA. At the free surface, the pressure is PA. If you go deep to deeper, the pressure will rise. If you go deep to deeper, the pressure will rise. That is the concept is coming here. This concept is coming here. The most important formula, if you go from the free surface, if you go downwards, your pressure will be rising continuously. And what should be the rise of the pressure? Rho GH. Initially it was PA, so how much the pressure change? Rho GH. So P minus PA is equal to rho. That is the gauge pressure. One concept the gauge pressure will gives you now in details. After getting this concept, what is the gauge pressure and vacuum pressure, just I am telling it. So absolute pressure, three types of pressure you might have heard. Absolute pressure. Absolute pressure means what is the actual value of the pressure. So this line you consider is the reference line. Reference line. Reference, this is the atmospheric line. Atmospheric pressure is at here. This is the reference line. Sorry. So from here you're considering atmospheric pressure is PA. There is some value 1.013 into 10 to the power 5 or Newton per meter square. Don't confuse with this. That means 1 bar or 1 atmospheric pressure. So atmospheric pressure sometimes we are taking as the reference. And which pressure is above to the atmospheric, this kind of thing we are telling at the gauge pressure. Gauge pressure. And below to atmospheric, we are telling at the vacuum pressure. Vacuum pressure. So any pressure in relative to the atmospheric pressure, if this pressure is more, that means it will come a positive value. It is considered as a gauge pressure. If P minus PA will comes in negative terms, this is considered as the vacuum pressure. That is the concept is here. So gauge pressure rise. If you go deep to deeper, your gauge pressure will be rise in this manner. So P is equal to PA plus rho GH for constant density liquid only. Most important thing. If density variation is there, if density rho is varying, then what will be happen? But rho is varying with what? If you give the pressure, the rho is changing. If you consider the gas, ideal gas equation of state formula, if you remember, rho RT. Rho RT. So you consider isothermal fluid. Isothermal fluid. So isothermal fluid is T is constant and R is constant. R is characteristic gas constant. So it's also one. So P is linearly varying with rho. P is linearly varying with rho. That is the case of the isothermal fluid. Another thing is the adiabatic fluid. In case of the adiabatic fluid, the P and rho relation in this way. From the thermodynamics, you can be able to see. We are writing it P to the power gamma is equal to constant. The same way, V you can change M by rho. M is of course a constant. Mass is always constant. Conservation, constant mass approach. So in that case, two consideration will see isothermal fluid and adiabatic fluid. That two consideration we'll see now. So static compressible fluid under isothermal compression. Isothermal compression means, so P is varying, is constant. So at atmospheric, so P by rho is equal to P0 by rho 0, we can consider. P0, what is the P0? At atmospheric pressure. If you take PA, you can write it PA also. At atmospheric condition or at zero position. Your reference, some point. You know the P0 and rho 0 value, given values. These are known values. So P0 and rho 0 is both unknown values. These are the unknown values. What is your hydrostatic equation? dP dz minus rho g. So rho you can be able to write it, replace the rho. So rho you can write it down. Rho 0 by P0 into P. So rho you can write it down in this. You just change it. So from here you got the rho equation. So rho equation is coming rho 0 by P0 into P. Just change this here. These two are the constant, but P is not a constant. So segregate the P's in a same side and remaining part is 0. Now if you go for the integration here, so these are the constants, so it will come out. G is also, we are considering a constant, so it will also come out. This all will come out. So here, from some point, initially it was P0 condition, pressure. Now it coming some different pressure P. Whenever it was P0, let it be it was at 0. After that, it coming jet. So with the jet variation is the 0 to jet. If you're varying from the 0 to jet, your pressure is varying from P0 to P. Initial condition at Z is equal to 0, that is the initial condition. P is equal to P0 and rho is equal to rho 0. That is the initial condition. If you're varying the jet, what would be the variation for the isothermal fluid? Static compressible fluid. So remaining task is ln P by P0. It's just integration. I'm not stressed over the integration, just writing it down. Here. So P. So rho 0 by P0. What is rho 0 by P0? Initial this case, so P0 you can write it down. Rho 0 into RT. So rho 0 by P0, you can write it down 1 by RT. Just change it. G by RT into G. So the P value, P0 into exponential of minus G by RT into Z. That is the variation of the pressure and jet here. Whenever in case of the isothermal fluid. If the fluid is adiabatic in nature. If the fluid is adiabatic in nature, this P by rho to the power gamma is equal to constant. The same way, initial condition you set up at Z is equal to 0, P is equal to P0 and rho is equal to rho. So hence here E by rho to the power gamma is equal to P0 by rho 0 to the power gamma. Remaining task is the same way, dP dz minus rho g, that is the hydrostatics law. So here rho you have to replace the rho. How to replace the rho? Because you just write the equation opposite in reciprocal form. P0. So rho is equal to rho 0 E by P0 power. So you just here put it minus P0 P by P0 to the power 1 by gamma. Then again segregate this thing. So it will comes in this manner, dP by P to the power 1 by gamma. Rho 0, 1 by P0 to the power 1 by gamma. G. Remaining task is the simple. Just you do the integration and put the limit. So here if you do the integration and put the limit, it will come. So what it will comes? So it is a P to the power minus 1 by gamma plus 1 minus 1 by gamma is equal to minus rho 0 by P0 to the power 1 by gamma G plus some constant. We have to find in searching for the constant. What is the constant? So constant term searching at Z is equal to 0, P is equal to P0. You put it this 0, so C will comes at P0 in this manner. C will comes P0. But before you have to write it, the equation P0 is equal to rho 0 for T0. Here temperature is changing, initial temperature is not the same, so T is equal to T0 as the initial temperature. Here temperature is not constant. Mind that. As with the Z, the temperature is varying. If you change the Z values, the temperature is changing here. That is the natural case. In the layer-wise troposphere, stratosphere, ozone layer, everywhere, if you go, the temperature is changing with the height. The rate of change is known as the lap state. We are going to finding out from this equation the lap state values. So this is the most important thing in here. So P to the power gamma minus 1 by gamma minus 1 by gamma is equal to minus P0 rho 0. Here rho 0 by P0 to the power 1 by Z plus C. So C will comes as a P0 gamma minus 1 by gamma. So that will comes in the P0. So P0 is coming, C value you are getting it. So P gamma minus 1 by gamma is equal to P0 gamma minus 1 by gamma. You reduce this equation, just nothing else. No such thing is here. Gamma into rho 0, P0 1 by gamma. That is the consideration. So if you take here, the P0 is the common. If you take the P0 is common here, P0 to the power gamma minus 1 by gamma, you take it common here. So what will come? Gamma minus 1 by gamma. So if you take it common, what will come here? Because that is side is only. So what does it mean? What does it mean here? So this term gamma minus 1 by gamma is nothing but 1 by 1 minus gamma. So already here P0 to the power minus gamma is there. So up and down, if you multiply one P, you will get it. So rho 0 by P0. Yes, you're just taking the common from here, nothing else. So this thing. So P0 gamma minus 1 by gamma, 1 minus, this thing is coming as a gamma minus gamma, and P0 by rho 0, rho 0 by P0. So G by RT0 into Z. This is the equation is coming. Hence, if you write it in this manner, so your equation, what it is coming, that would be P to the power some values minus P0 into 1 minus some terms is coming, something into 1 minus something into Z to the power gamma by gamma minus 1. This will come in this one. Same if you convert this thing. So P is varying in this way. Again, if P to the power gamma minus 1 by gamma, P0 to the power gamma minus 1 by gamma into 1 minus some constant term into Z, it was like this. So what does it by P and T relation in the adiabatic compression? The P and T relation is like this. Some constant term by Z. So with the Z variation, you can see the temperature variation. And whatever the constant is coming, it will come as a lapse rate. It will come as a lapse rate. So this way, we are approaching this kind of the things. So we have seen a lot of things. If there is a variation in rho density, and density variation is whether it is isothermal or adiabatic, will get such a way. So that's all here. Next topic we'll see later, the force exerted over this content.